Okay. Alrighty then. Let's get started, everyone. Okay. Hello, everyone. Thank you for joining us this evening. This is the Robotalks Fall 2020 presentation seminar. And this is going to be hosted by the Viking Robotics Society. My name is Anthony Bruno. I'm the president, or the current acting president, for Viking Robotics Society this year, and I'm also going to be today's moderator. So before we get started on our topic today and introducing our speaker, I'm going to discuss a little bit about today's topic. And so today's topic is going to be basically, for the most part, going to be computer vision and computer vision applications. And computer vision is one of those technologies or advanced technologies that are becoming cutting edge, and they're being utilized in plenty of applications and in different industries. And we'll see examples of those. As you can see on the screen, we're seeing computer vision being utilized in very complex urban environments, especially cities, where these systems have to be able to identify moving cars, people, logos, and other moving objects within this environment, and be able to identify them and essentially work with the data that's been given. In addition to this, computer vision is also being utilized in healthcare industry, and more specifically with X-rays. And here's an example of computer vision being utilized to identify internal physical injuries or even internal physical symptoms of diseases. And because computer vision is on this sort of onset of cutting edge or leading edge, it's opened up the avenue for new opportunities and opportunities for newer research to come about. And so we can see computer vision being utilized for autonomous vehicles, mainly lane tracking or lane detection, as well as identifying other cars that are nearby in the autonomous system. Or more specifically, computer vision can actually be utilized to identify body structures and recognize and recognize essentially skeletons of individuals. So this is what is called skeletal tracking. We're also seeing things like gesture recognition and posture or pose recognition. And this is something that our speaker today, Dennis Matthews, knows all too well about. And today he's going to speak about, or Dennis is going to speak about, computer vision and computer vision robotics, how those two merge together, his work and what led him into computer vision, his experience in computer vision as well, also its applications, as well as the merging of computer vision and robotics and its applications as well, and potentially the future of computer vision. And so Dennis Matthews is actually an Intel research scientist. He works within Intel Labs Emerging Systems Laboratory. And primarily right now, he's focusing on cloud research and infrastructure. However, Dennis has also worked as a computer vision and robotics algorithm engineer. And this was influenced by the courses he actually took during his PhD at the University of Illinois. And these courses, of course, included AI, robotics, and in particular, computer vision. And so Dennis is a local boy from Illinois. He attended the University of Illinois and obtained a Bachelor's of Science in Computer Engineering, and eventually a Master's of Science in Electrical and Computer Engineering, focusing in digital validation. And then he decided to switch gears after this and studied a lot more computer vision and robotics and AI courses, and later attained a PhD in electrical and computer engineering. Throughout his entire education, he also had periodic internships with Intel, which eventually led to his current career at Intel, and more specifically working with Intel RealSense technology. And so one of his the projects that he's spoken to me about most recently is a utilization of computer vision and Intel RealSense technology to measure shipping box dimensions. And this is for warehouse logistics in general. And this has provided low-cost solution for sizing, optimized dimensional weight, and improved supply chain efficiency for shipping warehouse logistics. And so I'm actually really excited to have Dennis here this fall. I spoke with him earlier this year, and I'm excited to have him here to share his thoughts on computer vision and robotics and sort of merge the two together. And yeah, just basically excited to have him here to talk about this subject for Robotalks Fall 2020. So everyone, please welcome Dennis Matthews. Dennis?
Thank you.
I'm going to give you, I'm going to stop sharing and you can share your screen.
Okay. One quick thing, I think with this few people, I think it's definitely fine to ask questions.
Okay, yeah.
So,
since we don't have a lot of people, if you guys have questions, I'm assuming you're okay with this, Dennis, to just...
Yeah. I'm
okay, awesome. All right, awesome. Makes my job easier.
Yeah. Okay. All right, can everybody see my screen right now? Okay.
Yes.
Okay, great. So yeah, thank you for that wonderful introduction, Anthony. And so my contact information is there for a reason. So if you have questions, want to follow up conversation or chat about things, definitely feel free to reach out. I'm also, there's nothing in here that's private or secret, and so I could definitely share these slides. There's a few videos, and so if they don't really, if you're not able to see them, we can also, those will also be shared. Hey, in the background? No, it's fine. Sorry. So yeah, like I wanted to sort of structure this with past, present, future. The past and present are like definitely like how I got to what I'm doing right now. And just, before we I get into that, it's fairly haphazard. It's fairly like doing things that looked interesting and sort of, if you've watched Frozen 2, I have a toddler, so the next best thing, doing the next right thing. So, then we talk about the present, and then a little bit about what I think it will happen in the future, or some things that interest me moving forward. And so, for the science buffs, and especially like in the movie buffs, will recognize this picture in the middle from Space Odyssey 2001. So Stanley Kubrick film from 1968. And people that know the movie know that HAL came online in 1997 in Urbana, Illinois. And so right here we have a map of Urbana, Illinois. HAL is placed right on the engineering campus. And so University of Illinois in Urbana-Champaign has a really big, engineering department. I think computer science, computer engineering, both those departments individually have probably about at least 2,000 undergrad students. And then you start throwing in all the other departments. And so it's a massive university in the massive engineering college. And so, it's probably, I think about at least a mile in each dimension. But yeah, HAL came online at the University of Illinois. I was born over here at Carl Foundation Hospital, so literally right down the street from the engineering campus, and a lot of computing is over here. So with that said, the main reason, when you're born and raised in Champaign, Illinois, with such a big, it's a university town, people are constantly steering you towards engineering. There's a great engineering open house that they have every year, or generally have every year. And so there's a lot of influence and positive influence. And so you do start to get a little bit of that feel and get a touch of what engineering is. And it's a lot easier in this type of college town with the big engineering department. And so, I wasn't fully committed from kindergarten or anything like that. And so, but when I got to high school, freshman year of high school, I really enjoyed a computer class. It's still teaching some of like the basics like HyperCard, so pre-PowerPoint, early, like in really early scripting. And so my mom, spoke to the teacher at a parent-teacher conference or one day after school and said, hey, my son really likes this class. Is there any way he could do like a job shadow or like an interview or something where he can sort of see what, like what people in this field do? And lo and behold, they had a grant program. Or my teacher also worked for the National Center for Supercomputing Applications, so created Mosaic. So before Internet Explorer and Netscape and Chrome, there was Mosaic. And so this entity created that, and a lot of the predecessors for internet technology, they had a grant for teaching high school kids and for scholarship or for internships for high school kids. And so after freshman year of high school, I was working professionally at the new National Center for Supercomputing Applications and doing some coding and learning to get used to software. And so throughout high school, like I was working throughout the summers and when I could during the school year, I was working, like at NCSA and really, like understanding more about computing, getting comfortable with the programming. And so, it gets to the point where, you get to senior year and you're like, okay, where do I go? And so I applied to different places. I didn't say, like I wanted to stay at University of Illinois, but just like the familiarity with the campus, like I sort of like was already like working on campus, knew my way around, knew a little bit about the courses, and so I decided to do my bachelor's there, and then like was really interested, like, and so after like with that, I got started doing internships with Intel early on. So this is .com bubble, or before the .com, it's while the bubble is growing. And so internships were a lot easier, to find. And so I started interning with Intel after freshman year of undergrad. And, like a lot of times just, like those opportunities were, like we want you to do testing and validation, and like which like you're like these chips are coming out and you're trying to understand, you're trying to break them and find if you can find these flaws before you actually make them, and then eventually test them after they're done. And so like I was like I've always been interested in doing the design aspect and designing systems, but like and so so I got my master's in testing, had a lot of internships doing that. And then, like I eventually got to the decision point where I was finishing my master's and said, like, I really think I want to do the designing aspect. And people say, what, and so it's asking like, what do I need to do to that? And it's like, well, generally like get your PhD, like PhDs are doing a lot of the design. And so I decided to get my PhD. So this isn't like, I did not the best of career advice, and it was more just sort of making the decisions at each point for what was the next thing, like what was required for me to do what I wanted to do for the next phase. And so so I ended up getting all 3 degrees from University of Illinois. Like Anthony said, my family's from there, my family still lives there, and so it was nice being able to right down the street from campus. It's a college town, and so lots of things are focused around the university, but yeah, like it's so and quickly describe. One of my projects is working with Baxter, and so I do some research. I'll talk a little bit more about it with, but just to describe this picture. So my research was around motion planning algorithms for flexible devices. And so this is Baxter. It's one of the earlier versions for Rethink robots, but it's like a humanoid robot with 2 end effectors, two hands. It also has a whole bunch of sensors, but I was looking at how would we use Baxter to do like cable installation and like a cable chassis or a harness within a vehicle. And so, yeah, a little bit, like while I stayed in Champaign for school, I did get a chance to travel. And so I think the big thing about this message is internships. Internships are very, very helpful. I highly recommend, I highly recommend them. If you ever ask me, should I do an internship? My answer will be yes. until maybe like the last few semesters of like a PhD. But it was very helpful. I got a chance to see the country. So, like I said, born and raised in Champaign. But I've been able to be, like live in all the states on the West Coast, Arizona, Colorado. So you get a chance to see where do you want to live. And so, like eventually, like I think one of the nice things about engineering, robotics is you have some selection. You can, there's opportunities a lot of different places, but you have some choice of where you want to end up. And I like that flexibility that engineering provides. And so I got a chance to say, do I want to live in this city or would I like to live in this state? And so, like in addition to the technical know-how that you're going to be getting, you're going to be building skills. You're going to be seeing like what's really like what skills are making money. Like in school, like you're definitely learning skills that can help you to like you're learning to some extent the basics, but the internships are really showing like how do these companies get revenue. You're working on something that matters because like generally either money or it's got some type of social impact, but there's different priorities, and it's definitely like around something like a tangible result. So did a lot of internships, most of them with Intel. A lot of the earlier ones were in testing, but then did more sort of like system validation. So did a 9-month internship in San Diego when Wi-Fi was being launched. So 2003 when Intel was launching Centrino. So that was really cool to, the testing that we're doing was leading to like changes in code where you would see the changes in code happening the next day. And like these drivers, like they had a launch date that they wanted to make, which is the Big Ten basketball tournament, was when they had the ad space. And so like seeing how that drive to get a product out the door and all that, the validation is really cool to work with the product. But then, like I did want to work on design. And so that sort of led to PhD in robotics, computer vision. So as Anthony was saying, I wanted to design something, design new systems, use new technologies. The price of computing has been going down and continues to go down. And in addition to the computing, also sensing is becoming, like sensors are becoming more capable, and sensors are also becoming smaller and cheaper. And so, like RealSense is one of those examples where, like to get a 3D point cloud 10 years ago would have cost 10x, most likely 10x the price of what a RealSense camera goes for. But so I started with Intel. And I started a rotation engineer program, so it's still sort of not sure with commitment issues to some extent for a career. Where I wanted to get a feel for what are different technologies, what are the different things that Intel's working on to see where I'd fit in the best. And then sort of more commitment issues when it comes to choosing a career was there's a chance to have a 2-year engineering leadership program, and so instead of working like in a regular business unit, we worked with a team of 4 people where we were given the opportunity to go create a new business unit for Intel. And so in addition to the technical skills that we're gaining, so, I didn't have any experience working with 3D point clouds, especially dense 3D point clouds. And so there's technical, skills gained, but it also was learning how do you create a business. And so, even if you have the best technology, if nobody's willing to pay any money for it, you don't really have a business. It's more of a hobby. And so, we actually went through, like how do you charge money for this and in a way that's profitable for, especially you want it to be a win-win where it's a win-win for the consumer, but also a win for your company that's creating, that's trying to generate revenue. So after that, worked with the drone team with Intel, and then led to the cloud systems research team, cloud systems research of the emerging systems lab within Intel. And so most of this is, like most of, especially the professional career has been somewhat driven by computer vision, mostly computer vision, but also understanding robotics, understanding industrial, like industrial systems, and understanding like what does a robot, like in a manufacturing plant need, and especially that visual information. So yeah, we'll talk a little bit. So like with my research, you see my camera. So I am an expert in bending metal, or at least I was at one point in my life. And so my PhD research is all about motion planning for elastic devices or flexible devices. And so I have one in my hand. the strip that I use for most of my experiments for research. And so it's planning, how do I move from one shape to a different shape? But then you also have to worry about, you don't want to have instability, so big snaps. And so my advisor came up with a formulation, and so we do the motion planning using forces and torques. And so a little bit of a profound statement. If I know the force and torque, so with this planar strip, if I know the force in the X, force in the Y, and also the moment about the Z axis, I know the shape. So it's a unique mapping between the shape of the rod and the force and the torque at either one of these edges. And so instead of planning based on like where the end of the robot is, we're actually doing our motion planning algorithm. We're planning based on the force and torque that's being exerted on the strip. And so if there may be an eagle-eyed person that realizes something about this video, mainly like how the strip starts and ends in the same position. And so, you know, like that's why it's complicated. You know, like this is more complex than like planning paths with a link. If I have like a robot arm, you know, there may be two angle, like, you know, if you have two links on a robot arm, you may have two different ways to be at the same position, but, you know, like it's countable, you know, it's countable. If it's just one link, you know, if I know the position and torque or position and angle of one link, I know everything I need to know about that that arm's configuration. With this, you can have the same, you know, like the endpoints could be at the same position, X, Y, and theta, and have two completely different shapes. And so we look at how do you do the planning to move between these two shapes. And then the computer vision aspect, so that's the motion planning aspect of, you know, describing the state space. But then the motion planning aspect is, how do I know the shape of the strip, you know? And so, you know, like we have our model and our theory, but like we do use computer vision to do some of that state estimation. And so the strip here is, you know, what we're using. And so we do have these markers. And so we're using the tracking of these markers to provide some level of feedback for what is the shape and doing these measurements. And so, you know, the themes are, you know, like the computer vision is giving us like a direct measurement of how the strip is moving. But it's, you know, like it's sensor fusion where you do have a force and you also do have some type of computer or some type of visual feedback. And so, you know, like, you know, a big key with cameras, and especially, like I said, they're becoming smaller, they're becoming more inexpensive. It's you know, like it's becoming like a, you know, a cheap, inexpensive way to give you that type of feedback, allow you to do some type of control loop because you have a state measurement. And so, yeah, and so with that, you know, like talking about the research that sort of led me to Intel, and you know, Intel, you know, like it's at that time that, you know, like it's growing and like these different types of careers and buzzwords, you know, change. But at that time, Intel wasn't big in hiring roboticists. And like they had a lot of roboticists that would work in the fab, and so like they do like automation with a lot of automation within, you know, like for within the technical manufacturing group. But you know, like this is before Intel was really getting into like autonomous driving and other types of robotics and you know, like, and so I was sort of, you know, like it was sort of new. It's like, what do you do at Intel? You're a computer vision person, was one of the conversations that you would have in 2014, and that's completely changed. Any questions? I'll talk a little bit about like the career at Intel, what I've been working on at Intel. But yeah, any questions about, you know, paths to here, the past?
I have one. I was kind of curious what, since I'm starting my college career at the moment, I was wondering, one, what made you want to pursue your doctorate besides, it sounded like you said that you wanted to develop new computer technologies, but maybe more on a personal note, if something else. And
Yeah.
then two, what do you think the hardest time in your college career was?
So I think so the doctorate was like, I wish it was like I knew I was going to get my doctorate. Doctorate was also in part due to two of the times when I was graduating were in economic downturns, and like '03 .com bubble burst, 07, 08 financial collapse. And so every time I graduated, the economy was in the crater, and like grad school was a safe space. And so in all honesty, I feel like, like there's definitely people that say I knew I wanted to get my PhD from like from the very beginning. But it was more like, like I like what I'm doing. And the economy's pretty bad. Do I, like it's, like there's not a lot of job opportunities. I think I'll stay in this safe space of academia. Was definitely an impact. But then it was like, I think, like in addition to that, there was that interest in like being on the designing end, being in R&D. Like I did know I wanted to do R&D, and generally the feedback is, okay, you probably got to get your PhD. And a lot of times that's the feedback. Like there's people that, like there's people that don't have a degree that, like you can't, like are in, like you are indistinguishable from PhDs. Like, and so like the PhD doesn't mean that like you're the best that's ever been, or like it's, but I think the benefit to that is it does make you have a methodical approach, and you've solved a problem that nobody, like generally, like for PhD, you've done something that nobody else has done. Like you have experiments that nobody else can claim that they've done, or you've done something that nobody else has done, and that's pretty cool. And then you write a book, and it's somewhere on a bookshelf. But but it's there is definitely like a lot of cool aspects to it. And like definitely like like being able to see a problem and then really decompose that problem. It's not an experience that like you eventually maybe in professional setting, but it's not an experience that you get in undergrad, like a really deep problem, especially a problem that nobody solved before. Like, and mainly if you're doing that, you should be in a PhD. Like that's, if you're doing something nobody's ever done before, you should be starting a business or getting your PhD. And so like there's definitely the interest in solving problems. I was seeing that I was building skills with like with as I was getting more degrees. And I think though, like you start, like you quickly you can get to the point where you're like, there's so much more that I don't know. And I think that's like a pretty common path in college, where especially like senior year, senior year, you get to the point you're like, I can't take all of these courses, but there's all these things that are really like that are pretty interesting, and there's so much that I don't know about this field, and I'm still getting a degree in it, but there's so many classes that I like to take, and that just continues. I can get your PhD and you're like, there's so much more I don't even know about robotics, and I've done something, experiments that nobody's ever done before, but I don't know anything about 100 areas of robotics. And so like it's definitely, there's definitely mixtures. Hardest time I think was definitely like it's like you're definitely going to have to stretch and learn new things. I think the hardest time though is actually like finishing up everything, and so that mad dash to write a thesis, and then like write a thesis, and then like you may be like teaching a course, like you may have like some teaching responsibilities, or maybe like research responsibilities, and then you want to see your family. You want your family to see you and know that you're alive and doing well, and and friends and that, and then you also need to find a job, because like it's sort of like you're done, so why are you still on campus? And so you've got to find a job, which may require you to go do like interviews and go across the country. And so you're sitting here with a lot of balls in the air at the very end, but with the knowledge that you'll have your degree really soon. And so it's nice because there's a light at the end of the tunnel. You generally, when you're in that stage, you do like like you're about to get your degree, but still that last month or that time when you're trying to manage all of these things can be like it takes a lot of like you really just have to keep plugging away every day. There's not much else you can do. All these things have to get done. And so yeah, I think like that was probably the rougher time, and that's under the best case. Like hopefully everybody's healthy and everybody's doing well, but in some situations that's not the case. And so yeah, and so like finishing up, but then it's also like the best time because you're finishing up. And so like there's positives and minuses about that time. But I would also say though, like getting started is also difficult. Just mainly, I mean, like there's doubt, you know, like self-doubt is really easy in any field. And in engineering, you're always going to be next to somebody that's been doing this since they're 8 years old. Is a pretty common thing. And like, it's like, how did you get like a robot system when you're 8 when they didn't exist? Like, how did these people, like, how did you have access to, you know, like compiler knowledge and all this, you know, like all these libraries and tools like 15 years ago? You know, like I didn't even know this they existed. And so you really have to block that out to some extent and focus on your race and focus on your path, because like that person's working on their path and they're, you know, like I assume everybody on this call, everybody's going to be doing exactly what they love. They're on their path to doing what they love, and making sure that you say, you know, like, I don't know these things, but I have a path. I like where I'm at. I have a path. I'm going to do something that I love. And, you know, like being able to put on some blinders, sometimes you need to put on the blinders and block out what other people are doing. I do like the engineering field because it's continuous learning. It's, you know, like part of the Moore's law, but, you know, like, you know, or transistors of scaling, but there's technologies that are coming online now that like people couldn't even think about 5 years ago. And so there's always, like, even if you're the best at what you're doing right now, there's a chance your expertise may not be that worthwhile, because in 2 years a new technology comes and displaces everything that you've learned how to do. So, you know, like you never want to stay stagnant in engineering, especially robotics, especially computer vision. You never want to stay stagnant. And like, if you know, like, I think, you know, being comfortable learning, you know, like, and being comfortable moving in motion is a good way to be, good place to be. And so that discomfort that you have when you're starting up is a discomfort that I think you can use that to turn that into healthy energy, because you stay thirsty for that knowledge. And, you know, like when new technologies come, you want to learn them and stay ahead. And so, you know, like it's a health, it can turn into a healthy energy though. Starting up and being next to a whole bunch of people that have 10 years of experience, when, you know, that could be concerning, but it you know, it gets better. And then eventually that, you know, keeping that energy, harnessing that energy comes out being very helpful. And so like with this, you know, like I'm showing the Intel RealSense technology. So this is an example of one of those systems that, you know, in 2014, I think 2013, 2014 is when this technology started to be, you know, like to the state where other people could actually build things with it within Intel. And so but it's a two camera, it's a camera, it's a little module. I don't know if I cleaned up my office, so oh, here it is. But just to get an idea for the size of the form factor, but this gives you a really dense 3D point cloud. And so previous systems, a lot of times, you know, like people, you would use like SICK lasers. So SICK is a brand. It's a laser-based system, very, very precise way of getting a 3D point cloud, but it's also, you know, like RealSense camera is about $100, a SICK laser, some of these were $5,000. And so, you know, like a 50x, you know, change. And so, you know, like not as accurate as a laser, but, you know, like in a lot of applications, you don't need micrometer precision. You know, a few millimeters off is fine. And so, you know, the picture on the left is a little bit of a schematic. Picture on the right is showing what it looks like. And so I have a RealSense camera. I'm looking at some pallets that are up against a wall. So the wall is this orange in the background, some pallets. Let's see if you can move, if you move the pictures, you can also see, you can see what the scene looks like. And so there's a cone there that you can sort of see, that's that little orange circle. But yeah, so it gives you this 3D, it gives you, you can have a picture, you have a color picture alongside with the 3D point cloud. So you know exactly how far away are these objects. And so this is with the RealSense Victor team, our sponsor said, hey, go out and find a way to make money with these cameras. And so very open-ended problem. And so we talked to a lot of different groups. And I think the next slide will sort of show, but like, and so we eventually talked to some people, and they said, you know, like, hey, we actually have a big use for doing box measurement. And so like, I didn't even know this, you know, being an Intel employee, but like Intel does a lot of shipping. We have a huge supply chain management organization. And I don't want to put a number on it, but it's definitely easily hundreds, possibly into the thousands. But we have a lot of experts on how do you get like people that can tell you the cost to get a small box from Hillsboro, Oregon to Shanghai, China, or how that changes with the pallet. There's people that know these numbers. They know these, like, like they know all of these types of things. And what's the cheapest way? Do you send it with boxes? Do you send it as pallets? But a key problem is that when you do this much shipping, you often don't have the time to do measurement of each one of these boxes or each one of these pallets. It's an area that's still a lot of pencil and paper. There's still a lot of automation that's possible for this field. And so you're sort of seeing how it's done now, where people have people carry their tape measure around and they measure it. But then, like a lot of times there's errors that come from that, where a lot of people say, okay, I don't need to measure this because, they make some assumptions. And so a lot of people will put, this is 1 by 1 by 1 by 1, or, so it's a box that's, 1 inch by 1 inch by 1 inch, and it's actually a pallet. And then somebody may actually be checking that data and need that data for putting a pallet on a plane, and they're thinking they're getting a tiny box and they're getting a pallet. And so what's, surprising is how often that happens. And you're talking with the Intel supply chain people, they're like, oh, everybody has a horror story from, hey, there's this one time where we ordered this piece, but they transfixed the height with the width, and we couldn't fit on a plane because the dimensions that we gave them were incorrect. And so, Intel internally was had a huge use for this. And then a lot of our customers, a lot of our partners had the same use for this type of dimensioning technology. And so, just to sort of reiterate, I talked a little bit about the SICK lasers. So those are $5,000 a pop. And a lot of these measurement systems, they actually use 4 of these. And so you start at, usually, just $20,000, with just the lasers alone. And sometimes, you could easily get to some of these systems for pallets that are $75,000 to $125,000. And you see the parts that we need. We need a $179 camera and a Nook, and you could do it on cheaper Nook. But you're looking at $700 versus $125,000. And it's not for every, we don't have the precision, and we can't measure every single shape. But if you have a big pallet that's square and there's nothing interesting going on, we are showing the ability to drop the cost for dimensioning by 1 to 2 orders of magnitude. And so think if you're in shipping and you're building things with lasers, and somebody's able to do something like that, some of your customers can definitely adopt for 1 to 2 orders of magnitude. This is the type of shift, and this is why it's good to have that type of that energy of there's more I need to learn. I can't, there's good not to, want to stay stagnant, but this is also showing the power of computer vision, where, these problems are existing, where there's a solution that's out there that costs lots of money, or sometimes there's just not a solution at all. And, with some know-how, there's definitely ability to use technology, to use cameras to change that, and in some cases save a lot of money. And so, not necessarily a planned project. I was sitting at my desk. I got this RealSense camera. I got the first version, and I guess just talking a little bit about computer vision, I was thinking, okay, let's do background subtraction, easy algorithm, where I want to see if something's new in the scene. So I take the average of the background, and then I say, okay, I figure out the background, have some baseline, and I do subtraction for anything that comes in the scene. So if a bottle or a box comes into the scene, you're going to see some differences with the color pixels and also with the height pixels or the depth pixels. And so then after that, it's well, if I know where the ground is, then I know how high a box is, and so I can at least measure the top of the box. Just using transforming the pixels that are new onto the ground. And then so that gives just the height for the box. And then the last step is, how do I find the width and the length? And so did a little bit of playing around, noticed that the point clouds are a little bit noisy. And so I found a way to selectively throw out some of those points And lo and behold, we're able to get measurements that were generally within about 3 millimeters for a box, like for smaller boxes, and pallets was within about an inch or two for pallets. And so this work was done over the course of about 2 years, but it's the power of computer vision, like having applications, a mixture of, like being, thinking about how do you decompose problems and doing that problem solving. Linear algebra was my worst math grade in college, and this is what like I use. And so to some extent, I feel like I should be able to raise that grade. This shows a little bit about where this technology was shown off, and so it's really cool to see a concept you came up with be displayed at trade shows throughout the world. And then it was one of the, in some of these trade shows, it was one of the most popular exhibits from Intel IoTG. And so this came from, like our team of 4 people created, like this entire unit. And so after, we handed that technology over to a different business unit, and our team moved to the drone team. And so we'll talk a little bit, this is one of the applications that we're interested in. And so with robotics, with drones, one of the areas is doing inspection. And so like drones give you this ability, like where they can reach places that you can't get to, or you have to pay people a lot of money and insurance, a lot of money to get to. And so one of the benefits of drones is they can do inspections for antennas, but like you generally have some mixture of sensors where like you have your camera that you're using to take pictures, but then you may also need some type of sonar, and in our case, like a RealSense camera that's giving us our depth. And so I did some work where we were taking the RealSense depth data and annotating the color picture data. And mainly, like a pilot that's flying on the ground doesn't necessarily know how far away they are from an object. There's still a lot of sort of judgment and a lot of experience at space. There's no like explicit, hey, this tower is 5 feet away from you. It's sort of like gauging, but like if you have a large object that's far away, it looks the same as a small object that's close. And so using RealSense, we were able to find a way to annotate that color image. And so you'd have an indication of, hey, this object that you see in the color picture is actually pretty close. You probably want to back away, and providing that type of feedback to the user. And then in addition to that, while working with the drone team, so we're looking at how does the drone figure out where it's located at? And so like 2 of the examples here, one on the left is from Pink. And so they do warehouse drones, but when you're in a warehouse, there's not a lot of variability. And so like you have some different options for doing localization, so figuring out where the drone is and how it's moving, how fast it's moving. Mainly, like you can use the shells as fiducials to some extent. There's as some type of guide. Like, and a lot of times I don't really care, am I 10 centimeters of, like from the aisle, or I just care like about the column. So I'm in the column number 1, column number 2, column number 3. And so you can get that information from using like, so we do like I did essentially just a color thresholding, and then did a little bit of smoothing, and so that gives us a column and it gives us our height. There's a lot of other tools, so I'll just drop, optical flows. So there's a lot of technologies that you can use that you can help this drone figure out where it's located at. And so drones, a lot of times people think of drones outdoors, they have GPS or they have other types of signals. When you start getting indoors, you don't have access to that data. And so like drones have to figure out, like with their accelerometers, which can be noisy, and then there's accumulation drift. And so cameras are one of those areas, computer vision is one of those areas that can really help drones do localization. So there's an example on the left, and then we also have the TM2 or tracking T265, which is here, and mounted that onto a drone. And so that gives another way for the drone doing localization. And so it's showing the picture of I think that's the fisheye that's pointing down, in addition to some of the tracking. And so this is mainly just showing like computer vision for helping drones figure out where they're located at. They definitely weight is a concern, but definitely helps to have some extra sensors on to supplement an accelerometer. So sorry, this is a little bit more blurry. And so this is talking a little bit more about what I'm doing now. So data management, and Anthony, heads up, thanks for, like showed it a little bit. So medical imaging was one of the applications that was shown in. It's definitely one of those areas that, like it's important. It can help, it can save people's lives. But being able to do that and store that information is still an area that people are learning how to do, are constantly learning how to do better and better. And so we're looking at, like storing images along with the metadata. So the description information. And so that allows you to do types of queries of, I want to see this portion of the brain for everybody that's above 85 years old. And then you can create some type of baseline, and then you can say, hey, is there some type of anomaly with this person versus other people that are 85 and older? Or is that just what people's brains look like with 85? And so being able to store image information and description information, metadata information is still there's an area of research that's still very ongoing and still to some extent fairly new, but it has a lot of very, like real problems that can be solved with this. And so we're looking at how do we store this information? How do we ingest this information? In addition to medical information, industrial information that's coming from robots, but then you get into robots can create gigabytes in a minute. And how do you, like keep that, in some smart way where you can do queries that are quick, that you need, but then also keep, like have that information available. So every now and then you may have to do a query that goes through a terabyte of data, but how do you like make that the minimum? How do you make sure that that's rare? How do I store and cache data? And so we're looking at how do we, do this data management for more edge applications and more systems that, like you're going to be bombarded with data. And so you do have to understand memory hierarchy and understand how do you, like the trade-offs of how and where you store the data. And so brief by that, a little fast. And so definitely feel free to send me emails later. I wanted to talk a little bit about future. Any questions, or do you want me to? Yeah, any. Definitely have questions, and I don't have a hard stop at 5. So, and so future, mainly talking about things that interest me. If you were to see me present a similar talk in a year, these are 2 years or 5 years. These are areas where I can sort of say, told you this is something that was interesting to me, is what with the next set of slides. But it's a little bit talking about robotics. What are some really cool areas in robotics, computer vision that I find fascinating, that I also think, like there's room to grow. And so this is IROS 2019. And so I just pulled some of the workshops that they had from this is from last year, and I saw a little bit of a theme. So I see the advancements in types of robots. So like aerial swarms, so like like a lot of bio-inspired, and so what types of robots are people building? Then I also saw, like a theme around like sensing and how to like robots get more information and learn more about their environment and get feedback for how they're performing with a particular task. And so around sensing and a little bit cognition, but especially like perception. And then the last being more, like it's in, like this is a loosely themed things, but also like starting to the human interaction with robots. Like telerobots. So if somebody's in point A and like a robot's, like somewhere completely different, how do you like there's your data transmit time can make a difference. Like if it requires very precise actions and you're not getting your feedback fast enough. And so there's a lot of areas that are, like the human and robot interaction. And so these are sort of the themes that I saw from IROS. And so then that gave me I sort of went through I just sort of listed things I thought were cool. And then I saw a similar theme. And so I ordered, like some of these in that same way. So cyborgs, no longer sci-fi, these are real, and real to the extent of the Ability Hand Psionic, University of Illinois founder. He's in my research group, Adil Akhtar. And so, yeah, we're building hands, prosthetic hands that aren't expensive. Like previous like prosthetics are very expensive. These are, like they have versions that you could 3D print that are open source, that have tactile feedback, so whether you're squeezing a grape or a baseball. Like we have people that are having, like robots augmented, like that are providing them capabilities that they've lost. This like here is this is actually from Robert Gregg, grad student, friend from University of Illinois, and so he's at University of Michigan now. But yeah, like leg orthotics, and so we have the ability to I don't want to say replace, but we have the ability to provide people with some capabilities that they may have lost in like augmenting systems. This here is an exoskeleton. I think it's from Ford technology, but a guy has an exoskeleton that's helping him and helping with ergonomics. And so, like that's that human person interaction, but like also the form factor. Robots going into places where people can't go or probably shouldn't go. And so I pulled this from RealSense, the Falcon 8, but yeah, I think it a nice summary. In addition, there's the entertainment aspect, but a nice summary where a lot of times, like it's complicated, it's hard for people to go there. Insurance doesn't make sense, or it's just not safe. And like you do have these abilities for robots to go into places where you can't. And I think he even gets into us being in Oregon, like firefighting or doing surveillance and understanding what's going on in some of these zones, like flying into fires. And these robots may not be cheap, or but it's still it's better than having a person have to go into these sites. And so there's definitely a lot of cool form factors of thinking, how do we build these robots that can go into places that people can't go? You talked a little bit about microfluidics. You may want this is from a friend from University of Illinois, is in my research group, Aaron Becker. And so this isn't quite microfluidics, but it's like smaller robots. These are 2.5 millimeters, and they're doing the steering with magnetism. And so he's been doing this since we were in grad school. But idea is they want to steer these small robots to, or these we'll call them robots, to blood clots. And so this is showing sort of the anticipate, like the path, the planned path, and based on these parameters, how well you're able to control where this is. And so the microfluidics or small devices, there's definitely a cool research going on. And how do I control these tiny things? And on the other end, you have this interest in how do I control these big things? So SpaceX landing on a water pad, like roboticists and control people, or I mean, like you united in cheer. Because if you could finally sort of say, hey, I'm a control system, like people could say, I'm a control systems person, and this is what I do. I help spaceships land or rockets land in the water. And so having a nice tangible example is definitely something, and a lot of control theorists appreciate it. And then, like big robots, self-driving cars, like autonomous, semis is another area. And so you're seeing these small robots, you're seeing robots get bigger. And then swarms is another cool area where robots is a complex field, but then you start getting into multiple agents. And so instead of one robot, I have 2 or 3 robots. On the right, this is from the Olympics, when Intel flew at the Olympics. One of the hardest secrets I've ever had to keep was I saw this in months before the Olympics, and I couldn't tell anybody about it, but we saw some of the animations. But and so these are open loops. So we just say, hey, drone number 1, here's your flight plan. Drone number 2, here's your flight plan. But people are researching closed loop value, like closed loop research or closed loop control for robots, where robots have to do some figuring out where they are with respect to other robots. With drones is a common platform. And so how do these drones align so they fly in a circle, they fly in a square? And so there's a lot of research, around how do you do this, and applications are also a lot of times around surveillance or finding missing people, or some of these applications. And then now we start getting into more of the policy considerations for robots. And so policy and also checking them. And so neural networks, a lot of times you'll see the term machine learning, and a lot of times that's sort of meant to mean, people will sort of just mean that for some type of artificial neural network. Machine learning is much bigger than that, but a lot of times people use them as synonyms. And like with these, these are mathematical structures, been around since World War II, maybe I think World War II-ish. you know, like there's a lot that, you know, like it's a mathematical representation, but there's still more things that like people don't necessarily understand how they work. A lot of people that use them don't understand how they work per se. They train them and then they say, hey, I got a trained model, let's use it. And you know, like there's more research that needs to go into how do you verify that a neural network or your machine learning algorithm is actually doing what you want it to do and doing what it's supposed to do. And so this work is done, this particular paper done by a guy named Taylor Johnson. We taught together. He took and we shared, had the same office on campus. But yeah, verifying that these networks that people are deploying across the world actually do what they're supposed to do is an area of to do research. And then there's the security aspects. And then like the reason, you know, like the picture on the bottom is why this is important. And so if you're familiar, unfortunately, this is with the Uber self-driving car in Arizona that ran over a person. This is what the camera saw. And so most people would recognize what's going on here, you know, like in the algorithm didn't, and I think actually pulled the car to accelerate. And so, you know, like there needs to be some understanding in making these neural networks more explainable, or also just verifying like that they're working is an area for research that you know, like I think will be around for a long time. And then sensing, quick anecdote. So one of the areas that I thought I wanted to make sure to share this was like, you know, so robust sensing is, you know, like computer vision definitely provides a new way of, you know, detecting whether you're, you know, like for localization or in a lot of information that you can provide from that. But, you know, like doing sensor fusion and taking a lot of different sensors and making, like figuring out where you are, and using that information to make you more robust to different types of hacking or attempts. There's definitely more. There's a lot of work. There's a lot of work that needs to go into security for your sensing in these robotic systems. Like a lot of times, people sort of, you know, like assume that nobody's, like there's no adversaries in the system, and that's not necessarily the case. In the picture on the left, I at a seminar, professor from University of Texas, Todd Humphreys, came in, and him and his research group got to go on a yacht in, I think, in the Mediterranean Sea and deploy their research to show. And so he's presenting, like essentially saying, hey, GPS has some flaws. If you know what you're doing, you can spoof GPS and tell planes that they're at a different altitude from where they think they are, which is very bad, everybody agrees. And so he showed that technology off at South by Southwest, and a guy walks up to him and is like, hey, you want to do that on my boat? And so Todd Humphrey has no clue who this guy is, and eventually like looks him up, and yeah, this guy wants him to deploy that technology on his yacht. And so him and his grad students got to go and hack the GPS for this boat and show that, yeah, they're able to steer it off course where the boat thought it was going straight, but, you know, using their ability to spoof GPS, they're able to steer it to the left to the point where everybody could feel that it was going to the left. And I think the grad student used the line from the movie, Tom Hanks movie, like, I am the captain of this ship now, is what he told the owner for when that happened. So, yeah. So definitely making the security aspect, making sensors more robust, policy considerations, there needs to be research, you know, like with self-driving cars, like doing the math and like, you know, like, is it safe to move from left lane to the right lane? There's definitely mathematical formulations, and based on the environment and stopping speeds and types of cars and parameters, you know, like there's definitely ways to make autonomous vehicles more and more safe. And then, but like, what are the policy considerations? Can you, you know, like you eventually need to say, hey, these cars should not switch from a left lane and a right lane unless they can guarantee some level of safety and concern. Same with facial recognition. You know, like there's a whole talk that people could have about, you know, like this slide alone, but facial recognition easily. Like when should it be used? When should it not be used? How do you test and say, hey, my facial recognition software is good? You're seeing lots of horror stories where people are sitting down to take a bar exam and the facial recognition tool can't recognize them, and it's telling them to move into more light, or in, you know, like, and so there's definitely ways. There's a lot of research into those neural networks or however people are doing these things, and so the policy considerations, and so like the technology problem is hard, but then also figuring out the policy and laws and regulations around that, a lot of research, there's a lot of opportunities for research around that. And then integrating ethics and fairness, I did want to talk about, again, it's a little bit applies to the facial recognition, but like you're creating technology and that technology is going to be used. And, like it is important that you think about what are some of the implications for how technology is used. And so on the left, it's confusion matrix. So somebody, like a camera's looking at somebody's face and it says, okay, I think this person's angry. Well, in some situations, maybe they're sad, and in 3%, 3 out of these cases, they're actually excited. And so, like there needs to be some thought about, like what, like how, like generally your confusion matrix is not going to be perfect, but there needs to be some thought about like what level of error are we willing to tolerate with these types of things. And so, algorithms of oppression. I picked a book authored also in University of Illinois. There's lots of books on the space, but it's like when you're creating these computer vision algorithms or robotics algorithms, a lot of times they have implications with like real life implications, and it's important to think about what level of error are we willing to tolerate. If like our confusion matrix is perfect with women, but it's problem with men, like it's highly erroneous with men, or it works well with people, like they're 15 and under, but it doesn't work with people that are 16 and over. Like there needs to be that discussion, the policies. People do need to think about how do we, like how is this technology? Does it really work in the wild? When it has an error, does it erring for everybody in the same way? And so, like there's an area to computer vision that I think, sometimes gets glossed over, but a lot of people are focusing on what are these policy implications? Also, what are the policy implications? How is this technology used? When the technology has an error, how is it impacting people? Like, and those are those are considerations that people doing computer vision do need to take into account. And so questions. I got a little bit of time still. I owe you pizza. If you see me, like seminars should have pizza. And so if you see me on the streets, I owe you pizza, or yeah, feel free to hold me to that. But yeah, I feel like seminars should have pizza. They had pizza anytime I went to one. So anybody on this call, if you want pizza, I got you.
I agree.
Awesome. Yeah, that'd be great. So is this your final slide, Dennis?
Yeah, this is my final slide.
Okay, cool. Yeah. Yeah, so is there anyone that has a question? Andrew or Tin or Michael, do you guys have any questions that you want to ask?
Yes, yeah, sorry. So it sounds like from what I've heard, you have an incredible amount of experience with engineering and technology and robotics. So I wanted to ask you if, I know a lot of major corporations are really touching on quantum computing at the moment, and that seems like it's a very hot topic, especially for like the last 5 or 10 years maybe.
Right.
But do you, from your own personal opinion, do you think that that's something that maybe you will be able to utilize soon in the future, or do you think it's something that's incredibly hyped?
So first I'll say the hype is real the hype is real, as in quantum computers can solve problems that